We will continue our discussions on helicopters and forward flight. In a previous video, we talked about all the problems that is happening when the helicopter is in forward flight, how the dynamic pressure varies not only radially from root to tip, but also azimuthally as you go around and round. We talked about shock formation on the advancing side. We talked about dynamic stall on the retreating side. We talked about the vibrations it can cause. We also talked about the extra power consumption that may be needed. We talked about the blade may have to go through complicated dynamics. So there's a YouTube video in our resources section where we have a close-up view of the hub region of a coaxial rotor. If you watch the video, you would see that it's showing all the complicated things that are going on at the root, at the hub level, to control the system. So it's a massive problem. So we have to break it into several smaller pieces and tackle it. So the first thing we need to come up with is some idea of what is the inflow through the rotor. You may remember in hover, we first did the actuated disk model. Then we did the combined blade element momentum theory based more advanced model. So we will do that in two steps. One is an actuated disk based model. So that's what we are going to be doing it here. This model is from Glauert, the same person, the British guy who did the flow through propellers. He did a lot of aerodynamics work, Prandtl Glauert model, things like that. So we are going to look at the Glauert's inflow model, which is based on actuated disk theory. That means the entire rotor sees the same uniform inflow all over from root to tip. All the way, regardless of the azimuth, you're getting the same inflow. So it's a very, very crude model, but this is a start. So this is what we are going to get started with. So let's look at what happens. So this model is very simple, very back of the envelope type of an approach, developed by Glauert. It's purely based on phenomena, not on mathematics. So in other words, we take what we know about hover, try to extend it to forward flight. So we know how the actuated disk behaves in hover, Rankine model that we saw a long time ago. So we are trying to extend it to forward flight. Nevertheless, it gives a reasonable inflow velocity estimate as a good starting point. It also can be applied to flow over a wing. Then it turns out that it gives the correct uniform inflow for an elliptically loaded wing according to the Prandtl's lifting line theory. So we would not rigorously prove this because this requires some knowledge of fixed wing aerodynamics. So we will just focus on the model itself in this particular lecture. As we mentioned earlier, in hover, things are a little bit simpler. The rotor disk is producing thrust weight straight up. The weight is pointing straight down, so thrust equal to weight. How about the drag? This rotor is, as it rotates forward, it's being pulled backwards, so it experiences a rearward directed drag. Here, as this blade comes forward, it experiences a drag in this direction. So when you sum up all the drag over this blade, it equals all the drag over this blade, except this is pointing backwards, this is pointing in this direction, so you don't get any net drag at all on the rotor. So the only balance we have to worry about is thrust equal to weight. And there's no rolling moment, there's not too much lift on one side, too little lift on the other side, anything to worry about. So it's a very, very simplistic situation. Unfortunately, in forward flight, things change. The vehicle, as we mentioned, the rotor has to produce not only the thrust, but it also needs to produce enough force to overcome the vehicle drag. So when we talk about vehicle drag, we are talking about the fuselage, we are talking about the landing gear, we are talking about the empennage. These are all non-rotating components. They don't produce any lift. So you could think of it as a parasite drag, also the hub. Then the rotor itself may have some drag in this direction. After all, it's a solid surface. You're dragging through the air, so it's going to produce a resistive force in this direction. So all this drag needs to be overcome by a component of the thrust tilting forward. So thrust produces a vertical component to overcome weight. It produces a forward component to overcome the drag. So the force balance is somewhat more complicated, even without worrying about the rolling moments, pitching moments, etc. Just from the force balance alone, the disc has to be tilted forward. So we will talk about how does the pilot tilt the disc forward in a later set of slides. So the angle between the free stream and the rotor disc is called, by the way, the rotor disc is called the tip path plane because the tip is here, the blade tip is here. By the way, in between the blade is going to be flapping and doing all kind of crazy things, but we just take tip to tip. We call this tip path plane. This is the flight direction. So this angle is called the angle of attack of the tip path plane, alpha tip path plane. So if this is alpha, this is 90 minus alpha. Then t times the vertical axis will make an angle alpha tip path plane. So t times cosine of alpha tip path plane is the weight. T times sine of tip path plane would be the drag. By the way, the thrust vector, the weight vector, the drag vector all have to pass through the center of gravity so that the vehicle is balanced. Otherwise, you'll get an unbalanced moments. Let's say the thrust is pointing this way. It's pushing the nose up, the weight is pushing the tail down, so you're going to get a pitching moment. So to have no unmounted moments to occur, all the forces have to eventually pass through the center of gravity. Okay. So this is the simplified picture of the force balance in forward flight in some kind of a average sense. We know it's an unsteady problem, highly unsteady. So we are talking about a time average. That means average the thrust over a full revolution. Then this is the thrust you are producing. That has to obey these relationships. All right. Now, our actuator disc model for in a vertical climb had this picture. You may remember this is the climb velocity, capital V. At the rotor disc, we had a capital V plus a induced velocity, lowercase v. So some acceleration took place between here and here of the molecules. So the stream tube kind of contracts. You need less area because you have a higher velocity. So same mass flow rate, all this mass is passing through a more smaller area here. In the far wake, this velocity doubles it. So instead of a v, you have a 2 times the induced velocity here. So you have even higher velocity, even smaller area. So the stream tube is continuously contracting until it reaches some kind of an equilibrium position in the far wake downstream. So this is what was happening for a helicopter in hover and in climb. In hover, capital V is 0. In climb, the capital V is non-zero. Now we are going to apply this blindly to forward flight. Use the same model phenomenologically, that means the same phenomena to forward flight. So this is what Glauert did. So we'll blame it on Glauert if everything doesn't work out correctly. So what Glauert said was, okay, remember this picture here? Rotate it so that the rotor disc is parallel to the x-axis. Then the flow will be coming at an angle, alpha tip path plane, compared to the rotor disc. So I have rotated it. So this is the rotor disc. The free streaming is coming at an angle, alpha tip path plane, relative to the horizontal axis, because the horizontal direction is the rotor disc. Okay. Now, by the time you reach the cross the rotor disc, in addition to the free stream, you have an induced velocity, lowercase v, that has developed. Therefore, you get this orange vector plus this blue vector, which is the induced velocity. You get this pink vector. So this is the velocity vector crossing the rotor disc, if you will, okay, just above the rotor disc. In the far wake, the induced velocity has double. So you take the orange vector, which is the free stream velocity, plus 2v. This is the total velocity. We see this vector is longer than this vector, which is longer than this vector. So again, we get a contracting stream tube because the area is decreasing, the velocity is increasing, density times velocity times area equal to mass flow rate. I have drawn this as though it's an extremely inclined, but in reality this inclination would be only a few degrees. Okay, the orange line on this rotor disc, the included angle would be relatively small. Okay. So at the rotor disc, what happens is, this is the free stream velocity. It's got an angle of alpha tip-path plane relative to this. So the horizontal component is V infinity times cosine alpha tip-path plane. The vertical direction is V infinity sine alpha tip-path plane, because this angle is alpha tip-path plane. Now, if you add the induced velocity, the vertical component is V infinity sine alpha tip-path plane plus the induced velocity V. So that's the vertical vector. This is the horizontal vector. Therefore, the total velocity vector or total velocity magnitude is this squared plus this squared. So V infinity cosine alpha tip-path plane squared plus V infinity sine alpha tip-path plane plus lowercase v squared. Now this is the velocity. Now how about the mass flow rate? It's simply the density times this velocity times the rotor disc area. This velocity is more or less coming perpendicular to the rotor disc. I have drawn it as though it's at an extreme skew angle. But in Glauert model, this velocity times rotor disc area times a density is the mass flow rate. In Hoover, it was rho A times V plus V was the mass flow rate. Density times disc area times V plus V. So in our case here, the mass flow rate is density times disk area times this total velocity vector. How about the thrust? Thrust is mass flow rate times the change in the vertical component of velocity. Here is V plus 2V, here is V. So the change in the angle velocity is 2V. So mass flow rate times 2V is the thrust. Mass flow rate times 2V is the thrust. So we apply this as Glauert did in forward flight. So now the mass flow rate is rho A times this velocity times 2V is the thrust. So this is the equation that we have to solve for the induced velocity V. It's a nonlinear equation because this V occurs here, but it also occurs here, and this is a square root term. Therefore, some kind of an iterative process will need to be done. For example, you may initially assume this little v to be 0, then take 2 rho A, this thing in the square root to the other side, is solve for the little v. Then flow that back in here, compute the square root term, then solve for the new estimate of v, keep iterating until this converges. So we can get a converged solution as long as we know what is the thrust we are operating under, what is the disk area, what is the ambient density, what's the forward velocity, and what's the tip path plane angle. So several things needs to be known in order to compute the induced velocity v. Now this is a dimensional expression. So we like to do everything non-dimensionally if possible, because then we can extend it from a model rotor to a full-scale helicopter much more easily. Scale everything, make everything non-dimensional. Therefore, this T will be expressed in terms of the thrust coefficient Ct, like we did before. All the velocities will be divided by the tip speed. So this component of velocity is parallel to the rotor disk. So this is called an edgewise component of velocity. That means it's going from the disk edge to the disk edge, flowing in this direction. So it's called the edgewise component of velocity. So we will divide this by omega capital R, which is the tip speed. So that quantity is called advance ratio, mu. Alpha tip path plane is a small number. Cosine of alpha tip path plane is close to 1. So this is a crude approximation, but we may as well use these when we do computer calculations. Then we are going to take this lowercase v divided by omega capital R is our lambda induced inflow, which we have used in the past in hover, but now it is for forward flight. So the relationship becomes non-dimensionally in this way. Again, we can iteratively solve. Assume lambda is 0, take 2 to the other side, take the thing in the square root to the other side, solve for lambda I, Put that in here, recompute the square root term, take it to the other side, take 2 to the other side, solve for the lambda I, keep iterating on it. Or some kind of a Newton-Raphson iterative technique can be done. So when you do that, by the way, if the advance ratio is greater than 0.2, this number is bigger than this number or this number. So we can crudely approximate it as 2 lambda mu I. Therefore, your initial guess could be lambda I equal to Ct over 2 mu. So this is a good starting guess. Estimated or guesstimated this way. Put this in here, compute the square root term, take it to the other side, take the 2 to the other side, solve for the lambda I, iteratively solve for it. So let's draw crude solution versus iterative solution. How does it look? They look reasonably close to each other at high advance ratios. This is the crude solution. This is from the iterative solution. By the way, when advance ratio is 0, mu equal to 0, you get a lambda I from here, you get a lambda I here, so Ct equal to 2 lambda I squared. So lambda I is square root of Ct over 2, which is the hour inflow velocity. So we very monotonically and smoothly recover back our original actuator disk model. Lambda I equal to square root of Ct divided by 2 from our model. So we are going to stop at this point. So we have developed an inflow model. Now we can start talking about how much thrust is generated, how much power is generated, and all the other matters. So we will stop this video at this point.